Hello, everyone. We'll start in a few more minutes time.
Interesting.
We will wait for a few more minutes and we'll start. Thank you very much for your patience. Okay, maybe we should start. First of all, thank you very much for joining this seminar, ITS seminar series on smart infrastructure. I'm the host, Kenichi Soga from UC Berkeley. This is the third seminar in this particular series. And today I'm pleasure to have Dr. Jennifer Schooling. Her talk will be entitled Smart Infrastructure and Construction in the UK. Dr. Jennifer Schooling is the director of the Center for Smart Infrastructure and Construction, CSIC, at the University of Cambridge since 2013. Prior to this, she was research business manager at Arab. At CSIC, Jennifer works with colleagues in industry and academia to demonstrate how better data and information can be used to improve our understanding of infrastructure. Jennifer has contributed to a range of industry guidance, policy documents, and wider industry publication to raise awareness the need for digitization in infrastructure area. She serves on British Standards Institute and ISO committees developing standards for digitization in the built environment. For example, Jennifer was the lead author for the carbon reduction code for the built environment. Jennifer is a fellow of Institute of Civil Engineers and holds the title of Officer of the Order of the British Empire, OBE, which is part of the prestigious British honor system. In 2019, Jennifer was awarded the ICE, Institute of Civil Engineers President's Medal for service to engineering and digital construction. Jennifer, I know it's dinner time for you, 7 p.m. And we really thank you for agreeing to give a talk to our colleagues in the US. The floor is yours. I'll stop sharing.
Thank you very much, Kenichi, and I will endeavour to start sharing. There we go. Hopefully you can see my slides there, can you?
Yes.
Brilliant. So as you'll see, I am from a centre with a very similar name to the Centre for Smart Infrastructure. One of the major differences is the way we spell the word centre, however, because obviously we're in the UK. CSIC was in fact set up by Professor Soga and his colleague in Cambridge, Professor Robert Mayer, both eminent geotechnical engineers, 11 years ago now, Kenichi. And it was my great pleasure to join in 2013 to become the director of the centre. So today I'm going to be talking about developments in smart infrastructure and construction from a sort of UK perspective, but I have to confess a lot of what I'm going to be talking about will be from a CSIC perspective as well. So the general content of my talk, I thought it's always worth reminding ourselves of why infrastructure matters. Before we plough into all the wonderful technical stuff, we don't often stop, I think, and reflect as engineers why infrastructure matters to society. So I'm going to talk about that for a bit, infrastructure as a system of systems, and then I'm going to get into some of the things that we can learn from having better data about our infrastructure, and talk about some examples around whole life value-based asset management, digital twins for structural health monitoring, and the challenges around using digitalization in cities and delivering public value from digital programs. And then I'm briefly going to touch on how CSIC has been able to engage with and influence policy and also industry practice, because I think we're very lucky in the UK, perhaps because of the size of the country, that we can have quite direct influence on the way things are actually delivered in sort of the professional world outside of academia. So to start with, as I say, I'm going to talk about why does infrastructure matter. And I think the key thing about infrastructure is it enables us to have a sort of healthy environment in which to live and go about our work. So these photographs are pictures from Kibera, which is an informal settlement in Nairobi in Kenya. And the main reason for sharing them is to highlight what life is like if you don't have formal infrastructure. So here, these informal settlements have been set up or have sort of emerged over many decades often. And without formal infrastructure provision, what you end up with is images like this one on the bottom left, where you've got essentially sewage flowing down the centre of the street, And the building on the left-hand side there with its door open is actually a school. So imagine if you were having to walk out of school and that was what was in front of you. It's not a great conducive environment for learning. It's not a terribly conducive environment for businesses to set up, and it's certainly not a particularly healthy environment to be living in. So without good infrastructure, this can be what life is like. Alternatively, with amazing infrastructure, and apologies that this is a picture of New York and not of Berkeley, this is what cities with good infrastructure look like. They have green and blue infrastructure, so you've got a park in the middle of the city there. You've got well-managed streets, well-managed buildings. You've got good water supply, good sewerage, good power supply, and all of this makes our cities and our towns vibrant places to be, healthy places to be, places that attract investment, attract industry, create economic opportunity for people. That said, infrastructure doesn't have to be in such a sort of formal environment per se. So this image on the right-hand side here is actually a refugee camp in Jordan, which was certainly at the time and may well still be housing a large number of refugees from the Syrian civil war. The key contrast, I think, between that and what I showed you from Kibera is that this is still a somewhat formalized settlement. It has good infrastructure. It has paved roads. It has power. There are buildings of a sort. And so that is a much healthier environment to be living in, even though those people have, fled from very challenging circumstances and still find themselves in challenging circumstances. They at least aren't having to fight the challenges of ill health brought about by poor infrastructure, which gives them a much better platform to sort of rebuild their lives from. So infrastructure really matters because it creates or helps to create the environments that we can all prosper in. And if we reflect on the UN Sustainable Development Goals for a moment, the four I've highlighted in red here, access to affordable energy, clean water and sanitation, sustainable cities and communities, and industry, innovation and infrastructure are all very obviously contingent on good infrastructure. But actually, many of the other sustainable development goals are as well, as you can see with the ones I've highlighted in blue here. Good infrastructure helps to address poverty. It helps to address inequalities. If it's well designed, then it helps with responsible consumption and production. And again, if well designed and well managed, then it can help contribute to climate action. So infrastructure is really important to society. The other thing about infrastructure is it's pretty complex stuff. So often as civil engineers or transport engineers, we think about an individual asset, maybe a bridge or a tunnel, or a single system like a road system. But actually infrastructure is much more complicated than that and much more interdependent. So the thing we have to remember is that this complex system of systems comprises of water, transportation, energy, buildings, our information and communications technologies, and that these all interact with and support each other. So increasingly, everything relies on our information and communications technologies, but also, the water system relies on energy, the transport system relies on energy, often the energy system relies on water for cooling. All of these things are bringing services to buildings. The other key thing is that certainly in large parts of the world, these infrastructure systems have developed over, centuries, really. So in the UK and in the US, a lot of our infrastructure systems date back well over 100 years, some of them to 200 years, and they effectively need to be maintained indefinitely. The other thing is that these systems, although they are systems of systems, they weren't really designed in that way. They've sort of evolved and emerged. So they're quite complicated. It's quite complicated sometimes to understand all of the interdependencies between them. And the other important thing to remember is that every year we only add, in developed economies, we only add about 0.5% by value to this complex system of systems each year. So in the UK, we've got a number of huge infrastructure projects going on. We've got a big high-speed rail project. We've got a massive super sewer being dug through the centre of London. Each of these huge projects, although they are costing many billions of pounds each, are a small intervention actually on that much bigger system that they're going to be part of when they're finished. So we really need to think not just about the new stuff that we're building and managing, but actually about all of that existing asset base that we have, that is what is actually providing the services and the value to society. And these complex systems provide those services to enable us to live our lives, to go about our business, to have fun, and they basically facilitate well-being for us. Because they last for such a long time, when we're thinking about them, we need to take a whole life perspective of them. We need to think, if we're designing an asset or indeed maintaining an existing asset, how long do we expect this asset to be used for? If we are building a new asset, we need to think about the whole life carbon. So actually, if we invest a bit more material and carbon now, will that help us to reduce user carbon, for example, into the future? Or actually, might it have a very short life, in which case investing additional materials and carbon will be a waste of that carbon? How can we make the use of all of our infrastructure systems more energy efficient? And how can we make our systems easier to maintain? Because one of the important things is, we live in a resource constrained world and we live in a carbon constrained world. So every time we make an intervention on a system, we want to be maintaining our assets for as long as possible and keeping them functioning for as long as possible. So it behoves us, when we're designing them, to think about how we're going to maintain them in the future and make that as easy and as resource efficient as possible a process. So civil engineers have responsibility for designing, building, operating, managing and integrating our infrastructure and built assets essentially in perpetuity. This picture is an image of Liverpool, for those of you who are familiar with the city of Liverpool in the northwest of England. This is the live building. And one of the reasons I like this picture is it shows you a lot of very old infrastructure. So we've got some old warehouses down in the middle of the picture there, with a lot of very modern infrastructure. So we've got a telecommunications tower of some sort there. We've got wind turbines out in the ocean generating energy. We've got a port here, which is an active port bringing both passengers and goods into the northwest of England. So this picture really captures the complexity of our infrastructure and how it sustains our cities. So how can we use data to help us gain insights about our infrastructure systems? That's a very important question to answer. And if I could make my slides go on, there we go. So what do we mean by cyber-physical systems first? Cyber-physical systems are essentially systems where we use sensors and data from our physical assets. We analyse that, perhaps via a digital twin, which is the current buzzword, and we use that to make decisions and make interventions back onto the physical asset. So there's this sort of symbiotic relationship between the digital twin and the physical twin. And we need that data about our infrastructure to design it and construct it and to maintain it well and keep it operating efficiently throughout its life. So adding sensors to our infrastructure helps us to collect better data, collect it more often. So, rather than the traditional approach of people going and looking at infrastructure and taking notes, we now are in a position where we can capture digital data about our infrastructure consistently and potentially continuously, if that's helpful to us. And essentially, that's what makes up this smart infrastructure that I talk about a lot. And in CSIC, Centre for Smart Infrastructure and Construction, that I run, we talk about transforming the future of infrastructure through smarter information and using that smarter information, which we gain from the use and development of sensor systems, to help us with performance-based design, so understanding the real performance of our assets, to help us with transforming the way we build and construct our assets and the way we manage and operate them, and then also the way that we think about how infrastructure serves our cities and communities. So it's really these kind of four pillars underpinned by the use and development of appropriate sensing systems to help with data-driven decision-making. And I'm a big fan of Lord Kelvin, who back in 1883 said, if you don't measure it, you can't improve it. And he's absolutely right. If we don't understand how something is actually performing, how do we know whether we're making a difference to it or not when we either design things differently, construct them differently, or try and make them perform better? So very much in CSIC, we look at learning from real performance, so that we can reduce uncertainty, both in design, in condition assessment, in construction and in asset management. And also so that we can create infrastructure solutions to make our cities more resilient. And ultimately, we look at how we deliver knowledge, tools and approaches to help us to meet the three sort of grand challenges of our time around resource scarcity, the drive to zero carbon and the need for resilient infrastructure. Oh, and that bridge in the picture there, if you've never seen it before, is the Millau Bridge in France. I think it's one of the most beautiful structures in the world. And it is often sitting above the clouds, as you see in this photograph. So if you ever get the chance to go to France, try and pay a visit to the Millau Bridge. So using better data, I think the key thing I want you to take from this slide is there are so many sources of data in our world today, from systems that are attached and embedded on our assets, like strain gauges and what have you, to systems that are remote from our assets, and they can be as remote as satellites, capturing data from many miles up in the atmosphere. We can also use data about the processes around our assets, and we can use social media data, geotagged tweets and so on, to give us information about how our infrastructure is being used, the level of loading that it's seeing, and so on. So we don't need to constrain our thinking when we're thinking about data. All these kinds of data can give us useful insights. The challenge really, though, is not only using better data, but using data better. So the key thing in our industry is we are very good actually at generating data. It's not always digital data. Sometimes it's paper data. Worse yet, sometimes it's PDFs, which are not digital data, if anyone tries to tell you that they are. They're just digital paper. But the challenge is often data in our context is generated, looked at once, and then either archived somewhere that it can't be brought back from, or thrown away. So we don't gain insights from it. We don't learn from it by looking at time series of data to understand how perhaps the response of a bridge is changing, for example. So the crucial thing about digitalization and smart infrastructure is that we must curate our data. If you take nothing else away from this talk, please remember that data curation is crucial to being able to better understand our infrastructure. These assets, which we hope will last us for many decades, if not centuries, we really need to think about how do we manage data about them over the whole life cycle of the asset, so that we can analyze it, create models from it, and draw sense from it to inform our decision making, giving us better decisions and improved insights about our assets. If we have that better data, then there's a whole range of things that we can do. For example, in design, we can calibrate models so that we can end up with better resilience and lower resource use. For construction, we can improve the processes that we have in construction so that we reduce waste, reduce capital carbon, improve quality and delivery, for example. And then in operations and maintenance, we can take approaches around things like future-proofing, condition monitoring, and risk-based maintenance and management approaches. And in the smart city realm, we can really think about about the infrastructure needs that our cities and communities have. So for this talk, I think you probably hear quite a lot often about design and construction processes. So I'm going to focus on a couple of examples from operations and maintenance and from smart city systems for the rest of my talk. So whole life value-based asset management. Asset management is the discipline of creating value for your business or your enterprise from your physical assets. So whether that is a water company, or whether that is a railway company, or whether that is a bank sitting in a building in downtown San Francisco, it's about understanding how the asset brings value to your business. Now, for the big linear infrastructures like rail, power, water, and so on, clearly the value to the business is very much tied up in those physical assets that are being owned and managed. And this value is brought both through individual assets, if you look at the bottom here, at the individual asset or project level, and also at the network level. So we need to understand, for example, the budget that we have to manage a whole system of assets in order to understand what interventions we can afford to make on an existing asset. But likewise, we need to understand the condition of our existing assets in order to make sure that they continue to function within our network and continue to be able to provide the service. So I'm going to focus on bridges for this part of the talk, with thanks to my colleague Manu, who provided me with these slides, some work that we've been looking at around how we understand risk in asset management and how we take account of that in the way that we think about our need for maintenance and management of our physical assets. The challenge that we often have is that we don't know very much about the actual condition of our assets, and often with bridges, for example, certainly in the UK, they get an inspection every 1 or 2 years, which is essentially a visual inspection from a distance, and then every 5 years they get a principal inspection where someone goes up, gets close enough to touch the bridge and really eyeball it closely, but very few of them have any kind of monitoring on them. So the challenge that we have there is that these infrequent inspections mean that we have uncertainties in our decision-making processes, and it's very hard to generate a business case for monitoring infrastructure because we don't really understand the condition of the infrastructure in the first place. And because we don't have a systematic framework to manage this infrastructure under constrained resources, we are increasingly at risk, particularly in the context of climate change, of our assets failing. This slightly confusing looking slide is looking at how we can take an approach to risk-informed monitoring and management. So the key thing is that one needs to have a register of one's assets to start with, and one needs to be able to identify critical bridges. And critical bridges are the ones that are vital to the network. So they might be a node which, if it failed, would cut off part of the network or cause need for a very long diversion, or they might be a bridge that carries, for example, several mass transit routes. Once you've identified your critical bridges, then you need to do a strategic risk analysis about these bridges, which includes identifying all of the risks that the bridge may be subject to, assessing the consequence and likelihood of that risk, and the consequence of failure, for example, may well be safety in terms of fatalities and injuries, but all the way down to things like reputation. And likelihood is based largely on the condition of an asset and the conditions that it will be seeing in terms of environmental conditions and so on. So these elements of the risk assessment are really important. And I think I've highlighted reputation down here because often I think as engineers, we forget that if an asset fails, it's not just about the cost of reinstatement, it's also about the disturbance to the service that causes. So if a bridge fails, transport can't pass. If a water main fails, you can't provide fresh water to citizens. And so that comes with a loss of reputation and a subsequent loss of customers and potential loss of investor confidence, which means that it becomes harder actually to provide your service, maintain your systems and so on. But we're generally doing all of this within budgetary constraints. So we have to understand how to prioritize our interventions, part of which is involved with the risk assessment and understanding actually which bridges are most critical in terms of our ability to deliver service. So in terms of individual bridges then, you have your business policy, which is informed by, for example, national transport policy, a regional transport policy, any future scenarios that we may be considering, stakeholder expectations, etc. And inspection gives us a register of bridges which are potentially at risk, and our criticality assessment tells us which ones of those are most vital to our network. So that helps us focus actually which bridges we need to prioritise for monitoring. And once we get that monitoring data, we're in a much better position to understand what maintenance is required and when, and to carry out life cycle cost analysis. So sometimes an asset may need repair, but it might not absolutely need repair today. But what we need to understand is the consequence of, for example, delaying that repair, will it end up in a much more costly repair in a year's time, for example, if we can't schedule it in this year's budget? And that's all very important, but it's quite tactical. And what our asset management often doesn't take account of, and increasingly needs to, is the impact of challenges like climate change on the condition of our asset base. So I'm going to talk a little bit now about the work that Manu's been doing around future scenarios. This slide is called Water Everywhere because something we've certainly been seeing in the UK recently and also in the US is an increased number of severe storms and an increased severity of those severe storms. So in the last 5 years in the UK alone, we've had more than 2,000 flooding events on the railway, which has created more than 1 million hours of delays on that railway. And, you know, as is a fairly small country, so this is pretty significant stuff. 3,500 kilometres of our railway are at significant risk of surface flooding and over 1,000 kilometres from river flooding. So that's bad enough, but this could more than double in the next 50 years due to climate change. And the estimated disruption costs of that are around £23 million a year, just from the flooding itself. That becomes even more of a problem when we start to think about rivers and bridges. Bridges suffer from this phenomenon of scour, which is essentially where the bridge pier hits the foundation of the river, and then it sort of hits the bed of the river, and then its foundations go into the riverbed. Scour is what happens if high-speed water comes down and starts to wash away essentially the material around the foundation. So you can end up with a bridge pier that is no longer standing on solid ground, and therefore the bridge fails. And in the 150 odd years there, we had 140 scour-related railway bridge failures. And in 2020 in the UK, scour resulted in 10 full collapses and 30 partial collapses of local road bridges. So this is an issue that is absolutely happening. If you look at that top figure there, it's an average of about 1 bridge a year fails through scour on the railway network alone. And when we look at climate change, 1 in 20 bridges will be at high risk of failure due to scour by 2080. And if you look at this picture on the right-hand side of the slide here, this is a bridge collapse in a place called Tadcaster in northern England. And it's quite a famous bridge collapse because when it fails, as you can see, there's a lot of other infrastructure that it took with it. So our bridges often are not just carrying transportation, they're often carrying maybe gas mains, water mains, power cables, communications cables. And as it happens, I was at a meeting earlier on today with a chap who was head of Gold Emergency Command when the flooding that caused this bridge collapse happened. And he said that the local police force, so the county police force, the state police force, their main communications cables ran across this bridge. So they lost a lot of their communications capability. So when a bridge fails, often it doesn't just take out the bridge, the transportation, it takes out a lot of other critical infrastructure at the same time. So scour, as it says here, is one of the primary causes of bridge failure in the world. So how do we go about preventing or mitigating scour? Well, obviously we need inspection and monitoring. We need to understand the condition of our pier foundations. But we also need to think about how can we predict the future condition of the infrastructure. And as you can see on the right-hand side here, this is a cartoon of a bridge and its foundations. As the river flows, you see that you can start to get this undermining of the bridge pier. And what that does first is create a certain vulnerability in terms of lowered stiffness. But if the scour gets low enough, then it completely washes out the foundations. And changes in the magnitude and frequency of river flooding will change the river morphology and change its capacity to scour these foundations because it can transport more abrasive media with it, for example. And our national rail management organisation, Network Rail, has a scour risk assessment standard which has been deemed to be unresponsive to an uncertain climate future. So it's probably doing okay for today, but even in 10 years' time, this scour risk assessment approach is probably going to be inadequate to really understand the true risk to our railway infrastructure. So we've been working with Network Rail to look at how they can improve this, and the approach includes looking at climate predictions, carrying out hydrologic modelling and estimating the river flow discharge as a result, and using that to predict scour depth during flood events, so that we can at least have a scour risk classification and understand which of our bridges on a network are most vulnerable. That can then help us to prioritise our interventions around more frequent inspections, for example, understanding which ones it's most important to perhaps do remedial work on the foundations for. And the example I'm just going to talk through quickly here is an example of 4 railway bridges across the same river system, essentially. And these 4 bridges, the bridge in the orange location, the yellow location, the blue location, and the green location, the maximum flow rate at those bridge locations for a typical peak flow, as you can see, varies quite substantially. So we've got a bridge here where the peak flow that's seen is around 3.5 cubic meters a second, versus a couple of bridges over here that are up at the 23 cubic meters a second. So very radically different river flows. But it's not, that doesn't actually give you a good idea of the risk to those individual bridges, as I'm about to show you. So if we look at the river, the bridges standing in the green and the blue locations, they've got much higher peak flow rates. And if you look at the amount of scour that is likely to occur over a flood at that peak flow rate that lasts for different periods of time, what you can see is, so the bridge in the green location has 3 piers, and 2 of them have a foundation depth of about 1.4 meters. And what you can see here is that if a peak flow flood lasts for 48 hours, then there's at least a 10% chance, if not more, that one or both of those bridge piers will fail, which is pretty substantial. On the other hand, if you look at the blue bridge, you've got, even if the flood lasts for half a day, you've got a pretty sure chance that one of the piers on that bridge is going to fail, if not all 3 of them. So although those bridges are seeing very similar flow rates, the bridge in the blue location is at much higher risk of scour failure than the bridge in the green location, although the one in the green location isn't looking that happy either. In contrast, when you look at the 2 that are at the lower flow rates, you might think, oh, well, okay, they're probably fine because the other bridge is going to last, is going to outlive a 2-day flood. But actually, when you look at it, they've got much shallower foundations. So the scour risk for the bridge in the lowest flow location is still, you've still got a 10% risk of that pier failing if the flood lasts for 48 hours. And again, the one in the yellow location, you've got basically, if the flood lasts for more than about 12 hours, then there's a serious risk of scour failure. So that just gives you a sense of the fact that we need to understand the morphology of the river, we need to understand the weather conditions that we are expecting to get, and we need to really understand the condition of our assets, their design, how deep are these foundations. A lot of our assets in the UK were built in the 1850s. We don't have good drawings, so we need to have good ways of inspecting and understanding how they were built and what their current condition is. And most importantly, climate adaptation really needs to be part of our asset management strategies. We need to understand the impact of future climate on our existing assets. So I also wanted to touch on the use of digital twins for structural health monitoring. We are capable these days of gathering vast quantities of data about assets, and it's not always easy to handle that data and use it to gain actionable insights from. So we've been doing a little bit of work in CSIC, one piece of work on our relatively new civil engineering building, where we've instrumented quite a lot of the building. So we've instrumented the steel frame of the building, we've instrumented the ground source heat pumps, and so we've instrumented the 2 boreholes, and actually we've dug a dummy borehole in between them so that we can measure ground temperature. We've instrumented the blue and green roof, and we're streaming that data continuously to a website where we can actually then explore the data live and see what's coming off it. Now, this is obviously a recorded video because I didn't want to run the risk of trying to bring up a website in the middle of a talk. But what you can see here is that in streaming that data, we can then start to look at what's the impact that is having on the performance of the building. Now, the steel frame, as you would expect, is largely doing very little. You can see a little bit of tension and compression on the vertical upright there. What's perhaps more interesting is the ground source heat pump, so we have 3 boreholes here, the 2 ground source heat pumps, and as I say, the soil temperature measurement in the middle. The soil temperature measurement is this brown line, and then we've got the green and blue lines are the temperatures that we're getting from the heat pumps themselves, the water temperatures. And the reason for instrumenting this was we really wanted to understand how well all of this was performing and whether there was any danger, for example, of us saturating the temperature in the ground, making it impossible for us to then use that for heating and cooling, because we have the aspiration across the whole of our West Cambridge campus, where this building is sited, to actually move to ground source heat pumps as a renewable form of heating and cooling. The other digital twin project that we're actively doing at the moment is the digital twin of this bridge. So when this bridge was built about 5 or 6 years ago, CSIC was involved in instrumenting essentially everything on it. We installed fibre grating sensors, we installed continuous fibre optic strain sensors, and since then we've installed accelerometers, cameras, and so on. And we are continuously streaming data from this bridge now. It took us a couple of years to get the power installed to enable us to do that. But we're continuously streaming data from this bridge. And this is a video that my colleague took yesterday. In fact, you can see 17th of March, where Miguel was basically doing this to show us that you can look at every single train that passes. So we're counting the number of trains per day, and for every individual train that passes, we're capturing strain data, we're capturing video data, we're capturing accelerometer data, which is helping us to characterize the behavior of the bridge. And all of this is being streamed back live to Cambridge. You can see one of the cameras has fallen over and we can't get to it to make it upright. So if you want to see what's happening with that train, you have to turn your head over. But essentially, we have motion sensors which on the laser rangefinders, which trigger. And the purpose of the laser rangefinders is to enable us to make sure that we capture the data that's of interest. Because as you can imagine, if there's a train every half hour, there's an awful lot of data being streamed that's essentially telling us nothing. So we're using the rangefinders to trigger the data capture so that we're only streaming back the data that's of interest to us. Otherwise, we would have, gigabytes a day coming off the bridge. That then is, if I can make the slide change, is streamed into a digital twin where the data is analysed to give us information, for example, about the strains in the girders, the dynamic behaviour of the bridge, what its response to vibration is, and so forth. And ultimately, that data can then be fed into a finite element model to give us more detailed information about the condition of the bridge. So this is just a sort of small snapshot into the kinds of things we can do with live data, and the ways that we can make it comprehensible to humans because the quantities of data that are being streamed, we couldn't possibly deal with in any other way. And this brings us on to my last topic, which is smart cities and delivering public value. So the reason I wanted to talk about this was that once we get beyond measuring the characteristics of an engineering artifact like a bridge, people start to become involved in the data capture. Data starts to get captured about us as well as about the things that we're using. And it's important in the context of cities and governance to think about what is the value that we're trying to deliver from any digitalization activity that we might carry out. So there's an organisation in the UK called the Centre for Digital Built Britain, which produced this very helpful document called the Gemini Principles, all about actually sort of what are the values on which we should base the use of digital twins. And they have these 3 key elements or key sort of legs to the stool, if you like, that digital twins must have purpose, because if they don't have purpose, then they're just a toy. They must be trustworthy, so they must be built on data of appropriate quality. They must be secure whilst being as open as necessary to enable data to be shared appropriately, and they must function effectively. And that function includes the fact that digital twins must be able to be federated, so they must be able to share data in a connected environment, they must be curated, so they must have clear ownership, governance and regulation, and they must be able to evolve as technology evolves. Because we live in the world of smart infrastructure, we live in this world with a slight tension between the physical assets, which have a very long life, and the digital capabilities, which evolve very, very fast, much faster life cycle than our physical assets. So the monitoring systems that we create, the digital twins that we create, need to be able to evolve as that digital technology improves. So crucially, digital twins in cities in the public realm need to consider that they are there to create public value through responsible digitalization in the urban built environment. So this is about both the things that we need to know, so having technology to enable us to capture data with an empirical focus on the built environment, but also the fact that we need to have governance and ethics involved in this. So in the past, often digital twins in a city context or smart city initiatives have been all about governing through technology, but we need to think about the governance of technology as well. That said, they can be incredibly useful and flexible tools. So one of the things we've done is look at a digital twin for the city of Cambridge, where we have a number of challenges. It's a city that's growing very fast. There's a lot of investment in jobs and housing. Thereby, we have a lot of congestion, which brings with it air pollution. But we also have a constraint in our energy infrastructure. So our energy grid is close to its capacity. So some of the issues that we have is, well, how do we reduce congestion? Do we do it by reducing car use and increasing public transport use? Do we address pollution by making all of our cars go electric, for example? And how do we think about where we put jobs and housing in order to minimize the challenges that all of this produces? So my colleague Lee created a digital twin of Cambridge, which draws upon information about the transport system, the energy system, the air quality system, and land use. But it's a sort of model of models that sits above all of those models and enables us to do a certain amount of scenario exploration in order to inform future policy, for example. So we looked at the impacts of teleworking, the future charging demand from electric vehicles, and the link of commuting demand with air pollution. I'm very quickly only going to talk about one of those because I realise I'm running out of time. So the electric vehicle charging question was an interesting one, because we looked ahead to 2050 and the projected the projected housing and the projected jobs in the future, and therefore the projected commuting journeys. And what we wanted to do was look at if all of those vehicles are electric, which legislation says they are going to have to be, what implication does that have for the electricity network? And we looked at the case of if all vehicles charged at the workplace versus if all vehicles charged at home. And what's interesting about this is the different scenarios actually bring stress into the grid in very different places. If all vehicles are charged at the workplace, as you'd expect, there's quite a lot of stress on the grid in the city, so within Cambridge and in the city of Peterborough. If all vehicles are charged at home, however, you can see that there are actually some fairly stressed parts of the network outside of the towns and cities. And what this does is enable us to look at policies around how do we create investment in the electricity grid, and or if we can't afford to create investment in the electricity grid at a particular time, how can we use policy instruments to encourage people to either charge in the workplace or charge at home or do a mixture of those things to manage demand on the grid? So that's just a fairly simple example of the way that we might use digital twins in a city context. This particular digital twin had embedded in it not just the journeys to work, but also the socioeconomic profile of the people who would be living and working in different areas, so that we could start to wrestle with things like the feasibility, for example, of working from home. If you're an electrician or a nurse, you can't work from home. You have to go into your place of work. You may well be working shifts. So, that needs to influence the design of public transport systems, for example. So digital twins are really helpful tools for decision making, but they must have utility. They can be used for things like optioneering and strategic planning, as I just showed. They can be used for evaluation and measurement. For example, how much material is in a given design? How is that reflected in what and how we build it, and so on? And they can be used for operational management or long-term asset management as well. So they're extremely useful tools, but we need to think quite carefully about how we design and manage them so that we can manage the amount of data that we're getting from them, as I showed in the bridge example, but also so that we can use them in a responsible way and in a well-governed way if we're doing that in a context where information about people starts to get involved. I'm pretty much out of time. I did briefly want to touch on how, as an organisation, CSIC has been able to have influence on both professional practice and on policy. So I will do that very quickly. One of the things we've done is do things in the real world to build industry confidence. So all of these pictures are CSIC researchers working in real construction and infrastructure environments alongside people from industry to test out the approaches that we've been developing. And that has made a big difference to the potential for industry to adopt our solutions. We've done an awful lot of knowledge exchange. We've done training, we've run conferences for industry. But the other thing we've done a lot of is guidance and input to standards. So we've written a lot of documents with the Institution of Civil Engineers, which is our equivalent of ASCII. We have developed methodologies and developed industry guidance for how to deploy those methodologies. And we've also written a number of sort of thought leadership papers and tried to have input to some of the sort of positioning things that come out of our National Infrastructure Commission and documentation that the Institution of Civil Engineers produces sort of on behalf of the Commission or to inform government policy. And, you know, we've produced a number of these papers over the years, both ourselves and in collaboration with others. And we're seeing them have increasing influence. People have been, you know, picking up the diagrams and the images and the explanations that we've used and starting to use these sort of forms of language and the thought processes that we have to change the way that things operate in the industry. And the most recent one of those is the Carbon Reduction Code for the Built Environment, which we developed last year and we launched at COP26, which is essentially a framework to enable organisations in the infrastructure and construction sector to make a public commitment to a path to net zero and to report progress on that annually. And then for the industry to work together in a collaborative way to learn lessons from each other and accelerate progress towards net zero. So that's kind of the story I wanted to tell. And I just wanted to finish by reminding us all again of where I started, which is the value of infrastructure and the reason that it's so important to manage it well and take good care of it. Thank you very much.
Jennifer, thank you very much. What a brilliant talk. I'd like to invite my colleagues to have any questions.
Thanks, Ben.
Andrew.
Yes, I have a question. First, thank you so much for your presentation. It's very inspirational to see the ways that data can be used successfully to sort of make informed decisions. One question that I have, and this might be more towards the US practice, just because I'm not familiar with how things have evolved in the UK, but a lot of infrastructure operators in the US are operating on very limited budgets. And so a lot of their asset management ends up either intentionally or not becoming reactive, where they save a limited amount of funds to fix problems as they come up, as opposed to trying to spend it proactively on things like monitoring. I was wondering if you could give sort of your opinion on how we move from, you know, these smaller research-based pilot projects that show incredible potential to something, you know, more on a large-scale deployment with infrastructure operators seeing the benefit and actually being willing to spend the money necessary to leverage these technologies.
Thank you very much for that question, Andrew. I think the first thing I was going to say to reassure you, but I don't think it is terribly reassuring what I'm about to say. UK infrastructure operators are likewise operating on very limited budgets. As I say, that's actually not very reassuring. But, the challenge often, I think the challenge is no matter how much budget you have, it will never be enough once you're dealing with a system that has assets of the kind of age that our infrastructure systems have. So, you could have an infinite asset management budget and it still wouldn't cover bringing everything up to, gold standard all the time. So that's where that risk-based approach to identifying where monitoring should happen comes from. Because if you can identify your most vulnerable assets and your most critical assets, so, if you've got a vulnerable asset, but it's in the middle of nowhere, and if you have to close it, it doesn't matter, that's one thing. If you've got an asset that's extremely critical, like the Minneapolis St. Paul Bridge collapse that happened, I don't know, 10 years or so ago, that severed a city and caused, obviously there was a very sad loss of life, but it also caused huge economic disruption because the two arms of the city were struggling to communicate. And we've had many more examples since the Minneapolis St. Paul collapse. So if you can identify the most critical bridges, then you can start to make a case for investment in sort of more ongoing monitoring on those. But it's always going to have to be targeted. And often, sadly, asset management companies struggle. Now, ours are, in the UK, they're regulated. I don't know if that's the case in the US. So they can ask the regulator for more budget, but they have to be able to speak with data. It's no good just putting your hand up and saying, I'd like more money, please, sir. You have to explain why you want more money and why that, why it's okay to increase charges to the traveling public and so on. So it's that sort of risk-based approach. How do we understand how vulnerable our assets are, and how important they are to us? I think. I hope that answers the question.
It does. Just a follow-up, and I don't want to monopolize your time, but do you think that the approach of doing these risk-based studies, is that better the role of engineering firms who are approaching asset managers as a service, or just because a lot of infrastructure managers, they're in the trenches and they're really just focused on getting through the next budgetary year, or managing what they have, and so they just don't always have either the motivation or the resources to do a risk-based analysis, which could pay dividends down the road, but right now might seem more aspirational than realistic.
So I think you're absolutely right. The people who are kind of in the trenches right now, it's very hard often for them to be responsible for this, and it's a strategic level piece of work. So it needs to be done by the asset owners, really, and or asset operators. The people who are responsible for allocating the overall budget, I guess. The people who are down on the ground trying to fix bridges, they often just don't have the bandwidth. They know what today's problem is. And often one of the challenges with, you do an interesting research project, we help someone monitor a specific bridge, that's great. You say, well, okay, so now what do we do about the next one? They say, oh, well, I haven't got time to think about that. I've got to go and fix this problem over here. So you've got to find the person in the organization with the level of seniority to be able to sort of stand back a bit and say, okay, how are we going to manage this going forward? And because ultimately they're the person who carries the risk if something goes badly wrong. The CEO of the company is going to have a problem if they're no longer able to deliver services. So yeah, that's the level at which the decision needs to be made that this is important. It's probably a level below. I mean, obviously the asset managers need to feed the information in, but they can't be wholly responsible for taking that strategic decision on behalf of the company. I think they need to be told which are the most critical bridges, and then they can go and fix those.
Yeah. Thank you so much.
Yeah, we have two more questions, but I think I'd like to have Claudio first. Our friend Claudio.
Thank you very much. Thank you very much, Kenichi. And thank you very much, Jennifer. It's for a fantastic presentation. Thank you very much. And it's always great to see what CSIC is doing. It's really impressive and inspiring. On that, I know I'm bringing the conversation from the UK to the US again here, but there is a large consensus at the moment on the fact that, of course, infrastructure are quite dated and need to be updated and improved and made better from a maintenance point of view. But why we do that and why we are thinking of that, of course, our society and our needs, as you explained, are under a big transformation. So we now are called to make huge investment on something without really knowing how this might be used into the future, right? Because you have all this transport infrastructure, but you don't know how many vehicles will turn to be electric and how many will turn out to be autonomous, and what would that mean in terms of needs for the road. And the population is growing and it's changing, and so actually huge investment, as you well know, are placed or are called to be placed here on something that will prove to be right or wrong in the long term without having that information. And I saw, and I was very thankful to see the future proofing part of your presentation and all the work you are doing. But I was wondering how the CSIC is thinking and evolving on this side, because that would be very inspirational to hear and to think about those topics from your perspective. Thank you.
So again, I think, you know, there's a real opportunity for those of us who like to play with digital tools in this space. Because, and unfortunately, I sort of ran out of time on the city digital twin thing. I could have spent an hour just on that alone, really. The opportunity that gives us is to play out potential future scenarios. I think we have to avoid the trap of thinking that the model predicts the future. It doesn't. It helps us explore potential different futures. And we can start to do things then like thinking about, well, okay, you know, what if we want to electrify all of our transport? What if transport becomes autonomous? And we can start to explore then what the future needs would be in those scenarios. You can start to understand which things are common across maybe all scenarios. So, you know, we know that if we want bridges, we need to maintain them. But, you know, if we want autonomous vehicles, do we have all of the sensing capability in the vehicle, or do we have some of it on the road? You know, how do we design our roads so that autonomous vehicles can run on them? You might, like me, be a bit of a skeptic about autonomous vehicles. I'm not skeptical about the need for electric vehicles, so we definitely need to crack the charging challenge. But we can affect the number of vehicles by encouraging people to share vehicles or use public transport, or, you know, there's a number of different ways we can solve a particular problem. And the problem is getting people from home to workplace. Some of us now work far more from home than we ever did because of the pandemic, and we've discovered that that's much easier to do. So, hey, why get out of your pajamas, sort of thing. So we can use those digital models to explore the potential futures, understand what the consequences are, not just for our cities, but also for the environment around it. So I didn't touch here at all on things like nature-based solutions for resilience and flood management and so on. But I think it behoves us to use those things to explore with the policymakers where we could go. And obviously it's not, the decision as to where we do go is one for society. It's not just for the engineers, but we're there to help facilitate that conversation and explain the implications of different routes, I think. Does that answer the question?
Brilliantly. Thank you very much, Jennifer.
Yeah, thanks, Claudio. I just want to have David Katze from East Bay Mud.
Yeah, hi, Jennifer. I absolutely loved your presentation. I thought it was just fantastic, inspirational, enlightening. I could go on, but I think you did a really, really nice job. My question has to do about with data. There's so much data we can collect. You know, and so for me, I work at a water utility. Have you spent time prioritizing what data is most critical for infrastructure owners to make better decisions down the road, so that we spend our money wisely in terms of, you know, building this smart infrastructure?
That is a really good question. Thank you, David. I think, you know, in the early days of if you like, the data revolution, the IoT revolution, there was a lot of sort of playing around in the sandpit, and people threw sensors at things just to find out what they could discover, you know, and, you know, do the sensors work in a rainy, wet environment with a digger driving over them every 5 minutes or whatever. But once you've done that exploring and playing, you really have to stop and stand back and say, so what is the problem I'm trying to address? What is the question I'm trying to answer? And design your data capture strategy to address that problem. And avoid the catch that we often get of people measuring the things they know they can measure rather than the things they need to measure. If you need to measure it and you don't have a solution for that, then go find a solution. Don't measure something else because you can, you know. So that helps with the challenge of spending money wisely. I think then the other thing is to come back to this prioritization piece of actually which assets are most critical, or which problems are going to be most impactful if they occur. So there's a very much a risk element to this. You know, as a water company, it may be one thing if something fails and you have a flood. It's a whole other thing if some kind of, if you end up providing non-potable water instead of potable water to households, so your level of risk is different depending on the outcome of something going wrong. And that then helps to prioritize where you invest your effort and your money. And then I think the other thing, so the thing that we're finding in the UK is we set up among the infrastructure clients, so the big water, utility, transport, etc. organizations, we set up something called the Digital Transformation Task Group. And representatives from each of these client organizations, we get them together roughly once a month, actually. And they share lessons and learning. And they're not in direct competition with each other, because it's electricity companies talking to water companies, talking to transport companies and so on. But they're all going on this digitalization journey together, and they're having different elements. Some of them have found solutions to some parts of the problem, and some of them have found solutions to other parts of the problem. And it's become a real kind of homework sharing club, as we call it. And so collaborating with other organizations to learn lessons from each other. Don't make the same mistakes someone else made, but then, copy the successful homework of somebody else.
Thank you. Thank you very much.
You're welcome.
Thanks, David. I know we have other questions. Maybe what we should do is 5 minutes past, we finish this particular session. And then if you want to ask more questions to Jennifer, maybe we can do it offline as when this particular recording is finished. But please join me, everyone, to thank Jennifer for giving up this brilliant talk.
Thank you very much for having me, Kenichi. It was a real pleasure.
I just want to share.
Nice to see some old friends.
I just want to share what's going to come upcoming seminar. It will be done by Professor Hyayong No, of Associate Professor at Stanford University of Structures and Sensors. So she will be talking fun stuff. How do we use sensors to understand how people use the infrastructure? So again, thank you very much. And Jennifer, thank you very much for joining us. I know you have to get your dinner right now, but thank you so much. And thank you everyone for joining, and have a good day.
Cheerio, everyone. Have a good weekend.
Thank you.
Jasong, if you want to join us, ask question, you can stay on, or maybe he's gone, or she's gone.
I'm here.
Yeah, okay. And I see Bing Yu as well.
Thank you so much, Dr. Schooling, for this fantastic presentation. I'm just curious, because I know in UK, the use of the ISO standard industry foundation classes has been pretty, advanced, comparing to other countries, US. So, yeah, I'm just curious, what would be your comments on this? Especially, I'm fascinated by your, digital twin and of the railroad bridge, where you can transfer real-time data. This is fantastic. But in this type of application, do you think it's gonna be the, can we build on IFC in the future, or how would that work?
Yeah,
just
for sure.
Any comments would be appreciated.
Yeah. So in the UK, we benefited from the fact that back in 2012, the government, in some unusual fit of wisdom, decided that they would mandate the use of BIM in design and construction of major new publicly funded projects. Mm-hmm. And what that basically did was make the construction industry sit up and go, oh my goodness, we better get our heads around this digital thing. And created a sort of across industry collaborative movement. So an industry that's normally extremely competitive started to have to collaborate on how are we going to do this. So industry foundation classes was one of the elements of that. That said, a lot of the big clients have sort of created their own data dictionaries. So for example, our National Highways organization has its own data dictionary, because it has, a nationwide set of assets, and it chooses to have its own ontology and its own dictionary and so on.
I see.
I think in some ways, it doesn't matter which data dictionary you use, as long as you use one. And you're consistent across your organization. Because the other thing we're finding, so I briefly mentioned in passing this line of sight guidance that we've been developing. And that's all about how to associate the information that you have about your physical assets in your asset information models and so forth with your organizational objectives and your organizational information requirements. And one of the things we're finding is, first off, a lot of organizations haven't defined their organizational objectives and information requirements, alarmingly. So how on earth do they do business? But even if they have them, it's actually quite difficult often to then understand how the physical assets are creating or helping to enabling the creation of that value. And it becomes harder the less important that physical asset is to the delivery of your business. So if you're a railway company, obviously the railway itself, it depends entirely on that physical asset. If you're running a hospital, obviously the hospital is kind of important, but you're probably more worried about the capacity of your operating theatres and whether your NMR machine is working and all those other things. So this piece of guidance we've written is to help people understand that. And what's emerging from doing the workshops on this is that often organizations have several data dictionaries and they don't all talk to each other. And they certainly have many asset management databases which have no relationship with each other. So kind of what this starts to do, though, if you start to think about what your information requirements are, then you start to go from what has been quite a bottom-up thing of, well, okay, we better specify everything because we don't know what's needed, to a system where you can start to be more efficient in your data collection. So kind of going back almost to David's question about how do we know what we need? Well, you start with what's your organizational objective? What are you trying to achieve? What's the role of your assets in helping to deliver that? And therefore, what information do you need to know about those assets to manage and maintain them and operate them in order to provide that? So essentially, as I say, it doesn't matter which data dictionary you use, and IFCs are a great place to start. If you don't have your own data dictionary, then please use IFCs because at least it's an internationally acknowledged thing. But if you do have your own, that's fine. Just be consistent about it across an organization, I think, is the main thing.
Well, thank you so much for your comments, Dr. Schooling. I don't know if you're aware, in the U.S. actually, the AASHTO, the national, the federal agency in charge of the highway and the road systems, they also established IFC as sort of the data standard. So now it's also across the states, different DOTs are starting to look at how to use IFC to manage the infrastructure. And I was actually doing some work with the local Indiana Department of Transportation. They are also in this process. So I really appreciate your insights and comments. Thank you so much.
You're most welcome. Thanks, Jensen.
Yeah, thanks, Jensen.
Thank you.
Maybe you will just want to say hello.
Yeah, I can say hello. I can ask questions. I can do either.
Hi, Jane. Lovely to see you.
Maybe it's going. It's still live, actually. So I'm not sure how much you want to say.
Did you want to ask a question then?
No. Maybe other people want to ask first, and then I can ask offline.
I think we're going to close soon. So you go ahead.
Yeah. So I think my question is like, so I'm just wondering, what's the speed or the intelligence of the digital twin system? And the reason I'm asking that is that because like with Kenichi, we're also working on like infrastructure related topics, but in the more extreme case, in terms of wildfire, earthquakes. And so this happened in reality as well. And then we see the infrastructure or the organizational thing failed. And then it has bad consequence, like the bridge collapse. And then in wildfire case, it's like people lost their lives. And then like we often see people cite the reason of it's out of expectation. Like we made plans, they made really good plans, but then what happened is out of expectation. So I think just comparing like what we can currently do versus what is needed, like so that like what is the current intelligence level and how can we go further?
Variable, I would say, is the answer to that question. I think some organizations do have very good data and they are not necessarily capturing it live at the speed that you need to understand an earthquake. But certainly, if you've got things like flooding, for example, you get the weather forecast, it's coming. You don't necessarily know quite how it's going to play out, but you can start to understand where your flood defenses are going to need to be shored up and things like that. So we have some levels of intelligence that are up to the job. But I think particularly I think what you're really talking about there is resilience and data to manage situations where things are going wrong.
Yeah, like get people
often in fairly short, sharp shocks, And we were having a CSIC industry partner strategy day today and talking about actually that challenge and the need to have very rapid access to data. And I don't think we've quite cracked that, partly because we haven't really thought through what kind of data we need rapid access to. But the other thing, and I think you guys did some really nice work on this, looking at how do you prepare for disaster. So it's much better to reduce the impact by being well prepared and sort of manage. So you did some work on how to get people out from wildfire situations, I think, and you modeled the transport network. And that was great, because what that did was prepare for a future event. So you didn't need to be looking at the data live, because you could say to people, okay, in the event that this happens, this is what you need to do. You now know this, go do it when that happens. In the event that that happens, do something else. And so you use the data to create a preparedness that means you're not having to respond in a panic, if you like. That said, there will always be situations where something unexpected happens, and we have to learn from them, and we have to think hard about what data we need at what kinds of speed and how we're going to get it. Because the other thing we were talking about today was, the more we rely on information communication technology, the more vulnerable we become to it failing.
Yes.
And that's a sort of cleft stick that we need to figure a way out of, I think.
Yeah. Thank you so much. Yeah. The reason is we are doing this, and then people keep asking, can you get us the real-time route, like a Google map for wildfire evacuation? And then exactly as you said, we think preparedness is more realistic.
Much more important to be prepared than to, but because the thing about a mass evacuation situation is you need to manage and control it. You can't have people making decisions to go left or right at the crossroads, because that just fouls the whole system up.
Yeah. And also the reason I'm thinking about that is like the different levels of automation of autonomous vehicles. So we have L1 to L5. Like for them, they are trying to get human out of the picture. But I think for infrastructure, it seems a bit different, at least. Like it's quite complex compared to driving.
Yeah, thanks, Mingyu.
Thank you.
I think Bernie wants to finish, maybe. Hey, Bernie, thanks a lot for organizing this. And Jennifer, well, thanks a lot for giving that nice talk, and all the questions answered were very nice.
My great pleasure. Thanks, everybody.
Yeah. Have a good evening. Yeah.
Bye-bye.
Goodbye. Yeah, thanks, everyone. Thanks, Bernie.
Bye.